Now we're going to introduce a whole new part of the course with a focus on modeling. So where does this fit into our data science life cycle? We've been working with the inference part of this part of the cycle, and now we're going to be moving towards the prediction part. Today we'll look at different models and loss functions. And in future videos, we'll look at simple linear regression, multiple linear regression, and we'll be ending with a topic of classification called logistic regression. So let's put this in the context of where we've been. The last few weeks, we've been focusing on populations and samples. In particular, we've had some set of individuals in the real world that we're interested in learning about, our population. But typically, we don't have the ability to gather data from the entire population. And so instead, we use a sample. We've talked about ways to make sure that you have a good sample in the sense that it's a random sample and representative of your population. And then we can try to make some inferences using the sample about the population. Questions of inference that we've looked at so far are hypothesis tests and confidence intervals. So for the rest of the semester, the predictive modeling is going to be taking the form where we observe pairs of data, and we are assuming they're representative of some underlying population of interest. Now we're going to be asking questions about prediction, association, and when possible, causation. So what do I mean when I keep using the word model? Well, in our class, we're thinking of this as some idealized representation of a system. Classic example is the simplification that we say an object on Earth will fall subject to a constant acceleration of 9.81 meters per second squared due to gravity. That is a type of model, but it doesn't account for a lot of other things. But in practice, it's accurate enough to be useful most of the time. So, keeping this in mind, our famous statistician George Box said basically all models are wrong, but some are useful. What are some reasons for building models? Well, one reason is going to be to explain phenomenon. For example, how are parents' average heights related to children's average heights? Or how does an object's velocity and acceleration impact how far it travels? In these cases, I'm looking to create a model that's simple and interpretable, where I am going to care about the terms I include in the model, and I want to be able to make some type of conclusion about the relationships between the variables. Other times, I may be more interested in just making accurate predictions. So in those cases, it's more of like what you'll hear called black box models, where a lot of times I don't even need to see the specific model or be able to interpret what's happening. I will just have some type of measure of how well it predicts, and that will be the only thing that I'm worried about in optimizing my model. These types of models are common in fields like deep learning, and we will be looking at creating models for this reason. A third reason is to make causal inferences. So this is a much harder thing to do, as we've talked about, because it really depends on your experimental design. And most of our statistical tools are designed to really infer association, not causation. In this class, we're going to be focusing on trying to balance reason 1 and reason 2. So yes, I want to be able to be accurate, but I often will want my model to at least be interpretable, and vice versa. There's lots of different types of models, but two common types I'm going to differentiate between physical mechanistic models and what we're calling statistical models. So by a physical or mechanistic model, I'm not meaning that it has to be related to some actual physics or something that you physically can see. but more that we have an understanding of the mechanism behind what's driving the data. A great example of this is actually Kepler's law, third law of planetary motion, and Newton's laws of motion and gravitation. So what do I mean by this? Historically, Kepler actually determined there was this relationship between a planet's period, squared, and its distance from the sun, specifically its semi-major axis length, cubed. What I've plotted here looks actually not like a square and a cube, it looks linear, because we've done a little trick to the data. That's something we'll talk about in future videos, but we've taken the log of both scales of the data, and then when you look at it this way, it appears to look linear in this log scale. We'll be using this trick to our advantage because it's often easier to transform data to have more of a linear relationship and then create a model. But what's interesting about the history behind this is Kepler noticed this relationship, but didn't have a causal explanation for why it was happening. It really wasn't until Newton's laws of motion and gravitation that you were able to take the physics underlying what was happening and explain this relationship. So this started with data and then moved towards more of a causal explanation as we understood more about what was going on. Not all things go in that direction. There's lots of times where we've started with the equations and then gone to look for the data. So Maxwell's equations of electromagnetism are a great example of that, where he predicted the existence of electromagnetic waves, and after his equations were published, people went looking for the first radio wave, and it was discovered after that. For our purposes, we're going to actually be looking at statistical models. And so what we mean by this are models where we come up with relationships between variables using data and statistical analysis. This is a useful skill in contexts where we may not actually be able to explain mechanistically what's happening, or it may vary. So there may just be some underlying elements of chance in what's happening. What I have here is some data from a 2010 paper that was looking at the relationship between patients who had a stroke and where in their brain the stroke affected most. So they were calling them lesions in the brain, and the types of effects that these patients saw in terms of their physical skills after having the stroke. And what they noticed is, while we do have a certain understanding of the neurology and mechanisms in the human brain, we really can't build an accurate mechanical model of every person's brain and know exactly what kind of damage they've suffered, model every neuron in the brain to predict their behavior. So instead of a mechanistic type of model, we looked at more aggregate coarse data based on fMRI scanners. And the authors of this paper did an overall statistical analysis of the data to find a relationship between the location of the lesions and the kinds of behavioral impacts they were observing. And so that's actually what's plotted here as an example of trying to find some type of relationship between the data. In this case, you're relying on correlations and statistical relationships in the aggregate, even though they couldn't pinpoint exactly what the low-level causes were. So those are two examples of different types of models, and for the purposes of our class, we'll be focusing on this second, these statistical models.